All right, guys, let's get started. So this is the 12:30 session of the PayPal track. This is PayPal under the hood. It's 12:35 and it's after lunch, so I expect some stragglers. And I hope you had your coffee because this is going to be technical and dense, which hopefully is a good thing. So my name is Chris McGraw. I'm the lead architect for the Payments and Credit Technology Group at PayPal. And I'm going to kick off with this. Lose a penny and everyone goes freaking crazy. This is kind of a funny story. A former engineer said this a long, long time ago because he was frustrated about how some other people were reacting to a bug he caused on a live site. He's no longer with the company, but I think it kind of sums up pretty well our culture and our attitude about how seriously we take transactions and processing things consistently and reliably. So this talk, there's three major sections. I want to give you guys kind of a sampler plate of what goes on behind the scenes at PayPal. I can't do justice to the whole system, but this is like the Chili's sampler platter of PayPal. I also picked a couple of problems that I thought were interesting in the PayPal space that I'll talk about the solutions to. And then I'll end up with some high-level philosophy that influences our design and some lessons that we've learned over time. So let me talk about myself a little bit. That guy in red is me, circa 2002. This is the PayPal engineering team way back in Mountain View. Were any of you PayPal customers back in 2002? 1, 2, good, excellent. Well, thank you for entrusting your money to this scruffy band of sort of ragtag hooligans. PayPal in 2002 was sort of stereotypical storybook startup life. You know, everyone lived at work, everyone was friends. When we released code to the site, we'd all pile into the office late at night and order a bunch of junk food. Egg rolls were kind of the favorite. And we'd push the code and then cross our fingers that the site would work, and usually it wouldn't, and we'd spend the rest of the night staying up trying to fix it, getting it back to how it was. Early into my employment, my then manager handed me a Post-it note that had some words scribbled on it. And I said, what's this? And they said, oh, it's the root database password just in case you need it. All right, surprising. This is like 2 weeks in. And it did actually come in handy for some of those push nights, fixing problems and fixing customer data that we had not treated perfectly well. So fast forward about 10 years, here I am now with my daughter. She's now the reason why I stay up all through the night. PayPal still releases code. It goes a lot more smoothly now. But junk food is still heavily involved. And you know, even if I wanted to, I wouldn't be able to touch our databases with a 10-foot pole at this point. And that's a good thing. So let me get into technology. I think it's important to sort of put PayPal's early days in context because it influenced our technology choices. And really that context is that the business was in a constant fight to stay alive. And there were really two villains in this story. One was online criminals. You know, PayPal was a new way of moving money around, and you didn't have to be face-to-face with a person. So the mob, organized or unorganized crime, found PayPal to be a pretty ripe target for exploits and attacks. And so as these guys figured out ways to exploit the site, the product development team would figure out ways to defend, and we sort of had this arms race constantly going on between the good guys and the bad guys. Fortunately, we survived that arms race, only to be challenged by someone less nefarious, actually eBay. eBay had a competing payment system, BillPoint, that they tried very hard to wedge into the eBay auction site and push PayPal out. This was much more above the board competition, but it was sort of a fierce force nevertheless. You know, at any moment, I think the wrong kind of policy choice from eBay could have just totally wiped PayPal off the map, and our main source of revenue and customer acquisition in eBay auctions would have just been out the window. So this, combined with a really smart, confident, aggressive early dev team, produced a lot of good things. So if you've ever heard of the Gauss-Levchin test, that's really the first implementation of CAPTCHA on a production website. But on the other hand, this also produced a lot of bad behavior. You know, no technique was too dirty or too off the table in the coding world, so we ended up with a lot of copy and paste code, a lot of projects that we sort of rolled our own infrastructure instead of being diligent and finding something off the shelf. A lot of magic communication between components, ending up with a code base that was more or less just like a giant ball of mud. So those forces really influenced the early days, and those influences stayed with us for quite a long time. So let me give you the quick overview of what PayPal looks like on the inside. We're a C++, Java on Linux shop with a web and API layer on top. Sits on top of a bunch of services, stateless services, which are also written in C++ and Java. And then we have two options for managing state. One is traditional, pretty big iron Oracle instances running on IBM or Sun. And then for transient data, namely data that's stored in memory and isn't persistent, we have an in-house solution called Mayfly. If any of you are biologists, then maybe you'll know that mayflies actually have a short lifespan. They're flies that die quickly, so transient storage of data. Let's talk about some buzzwords so that you can sort of go home happy. Most of our website runs on commodity hardware, so cheap pizza boxes running a stack of Linux, Apache HTTPD, or Geronimo in the Java case. Like I said, databases are Oracle and Sun. We have ActiveMQ and TIBCO installed as message buses used for slightly different purposes. And then our data centers, there's 3 of them, and a lot of the site runs active-active distributed across those 3 data centers. In terms of software frameworks, going back, a lot of this was built custom way back starting in 1998. So protocols for serialization, you can kind of compare it to Avro or Thrift or protocol buffers, same kind of deal. But in-house, a database-backed pub-sub method, which I'll get into later. Mayfly, transient data store. And then a whole custom build system, C++ server container, and Webflow framework is what drives a lot of our C++ websites. The Java development that happens at PayPal now is much more standardized in terms of utilizing pieces of the Java ecosystem. But rolling back, starting in 1998, there wasn't really a web ecosystem, at least in the C++ world. So were PayPal to start today, we'd have a huge array of infrastructure that we'd pluck out and not build ourselves. So in terms of what's inside, what the software actually does, you can think of it this way. There's a lot of work that goes on in servicing web requests for our customers, painting pages, dealing with web flows, customer interaction, likewise on the API. And then there's more or less, you can think of it, 3 basic capabilities that PayPal is built on. One is authorization, checking credentials, making sure that customers are allowed to do what they want to do. Then the wallet capability. This is where we store all the customer's sensitive financial information and then make it available in the context of a checkout or some other kind of payment use case. And then finally, payment processing. This is where we fulfill the payment that the customers request with us. This is the world I come from, so the rest of this talk is pretty heavily influenced by that. That's my worldview. So payments. Here's some pseudo SQL for how you might think payments work. You debit a sender, credit the recipient, insert some sort of transactional row in their history, and then you commit. And the database makes sure that all that happens or none of it happens. And this was actually pretty close to truth when I joined. But as time goes on, this whole picture gets a lot more complicated. Risk models, integration with foreign exchange, different limitations, refunds and partial refund offers. So the bottom line that I'm trying to say here is that the payment system, although in concept, it does a very simple thing. It maybe moves money from a sender to a recipient. Has all these peripheral concerns and all these other systems that it has to work with to ultimately produce one consistent outcome. Oops, sorry. All right, let's move on to challenges and solutions. There's 3 basic themes here: reliability, security, and scale. So reliable processes. This is really what's behind this concept here. How do you make sure that we don't just drop money on the floor and forget that it ever existed? Or vice versa, how do you make sure that the software doesn't just invent money out of thin air? That would not be good. So this may seem trivial, but I want to emphasize how much value we get out of standard relational databases, Oracle in this case. So when we have an application that does some work through SQL, we do some work, do some other work, and then we commit, what do we get at that point? What kind of guarantee is made at the point that commit happens successfully? So in our case, things happen like data is written to a redo log. This is a file on disk. It's got the raw activity log that that database performed in the case that that database gets horribly screwed up somehow and you need to recover. Likewise, data is actively replicated to a standby. So in the case that the primary machine goes down, we have a secondary machine that we can turn back on in only a matter of seconds and continue processing and continue servicing customer requests. And then finally, a similar replication strategy also occurs, but to an offsite failover. So in the case that a meteor hit our data center, there's an actual duplicate copy of PayPal able to run somewhere remote, hopefully without a range of that meteor. So in terms of patterns, I want to share with you guys a pattern that's pretty common at PayPal and serves as a basis for how we integrate different systems that have to manage different state, potentially in different databases. I pushed a button. So I'll walk you through this here. In this case, application A is working on its database, does some work, but step 3, it inserts a message and then commits. So in one DB ACID transaction, we get a message inserted. Application B is polling on that table and discovers that a message has been inserted. And then its pseudocode works like this. It has some work to follow on. So maybe this is sending a merchant payment notification. Maybe this is updating some risk counters. If locally there's no record of that message being processed, we continue forward, do the corresponding work, update that risk counter, queue up that merchant notification. We locally mark that message as being finished, and then we commit. And so the end result of this picture here is that if work happens in A, work eventually is guaranteed to happen in B. And the nice thing about this is that if the application B goes down temporarily, application A isn't affected. So we have a nice asynchronous boundary here that lets application A be the real focus for availability. So if any of you have done this pattern before, you might be aware that what happens if you want B's work to happen synchronously. So we can overlay this pattern with a synchronous attempt. After application A commits, it makes a synchronous call to application B's service, tries to do the work synchronously, and if it works, great, done. If not, if that communication fails somehow, application B will still end up reading that message and backing up with the asynchronous process. So with this, you have, in the green path, synchronous work being done in 2 distributed systems with a reliable backup. So this is a pretty common pattern at PayPal for how we get lots of our different systems with their different state managements to interact and play together in an eventually reliable and eventually consistent way. Well, in a totally reliable, but eventually consistent way. So security. It wouldn't totally be responsible for me to outline all the things that PayPal does for security. So what I'll do is I'll give you kind of a top to bottom view of things that I would consider to be pretty standard in the financial industry. So starting at the top, there's physical security. It's important that someone can't walk into our data center and waltz out with a hard disk full of customer information. So doors are locked, cages are locked. We don't publish the locations of our data centers. Moving down, there's machine access controls, who's allowed to SSH into what box and from where you can do that. Firewalls restrict network access to specific ports and specific machines as well. And then at the application layer, we implement service level access controls. So we actually have to specify that application A, in this case, is able to use the services of application B. It's not just a free-for-all internally. Then going further down, data is encrypted on the wire. This is like standard SSL that you might be familiar with. Data is also encrypted once it actually lands at rest on a disk or in a file somewhere. And then finally, hardware encryption can be used to push the job of storing keys and the unencrypted data into hardware that's presumably less vulnerable to software exploits like buffer overflows or Linux kernel problems. Push it out into a hardware component. So this works for people who aren't in the company. But how do you secure your system and how do you make it trustworthy for people who are allowed to touch these things? So let's talk about the example of customer balances. If any of you are familiar with using PayPal, you can store a balance with PayPal and keep it open. When I joined, my first question was, how do we know that I don't just go into the database and say, update Chris McGraw's row and set balance equals $1 million? There was an answer to that, fortunately. I think had there not been, my employment might have been in question. So it works like this. Every time we make a balance change, we journal that change in a log. So in this case, on October 1st, the balance was created, $0. On the 12th, we added $150 to it. On the 13th, we subtracted 50. That's why it's currently $100. So you can take these two views, sum up the left one, and it should equal the value in the right one. So in the case that someone tampered with that balance value, you discover it as a mismatch between the log and the counter. But now what happens if someone tampers with both? Set balance equals $1 million, insert a row into balance log saying, I'm giving Chris $1 million out of nowhere. So the chain kind of continues. We also have account activity, which talks about financial transactions at the next level up. So in this example, on October 12th, we explain that $150 came from adding funds from a bank. And likewise, those $50 were removed from the account because this customer sent a balance-funded payment. So now the balance log and the account activity table can be compared together, explaining why those balance log changes actually are there. And so if you follow a chain like this, eventually this comparison reaches a border of PayPal where money is actually coming in or out of the system from an external financial system, at which point it actually does need to be real money. And so this process of comparing one system to another and trying to answer the same question two different ways is ultimately how we build trust that there's no tampering happening in the middle. Because if there was, one of those comparisons would end up turning up to mismatch. All right, let's change gears. Scaling. Scaling is an interesting word because scaling what? There's a lot of things that need to scale as a business grows. In PayPal's case, things like payment processing capacity. When I joined, we were doing tens of payments a second. Now it's in the hundreds. Total lines of code in the code bases is a scaling problem on its own. The number of applications we manage, the number of developers that are sitting in our dev centers and committing code to our source code. These are all scaling problems that all have different solutions. But in my experience, all of these come up at some point if your company grows fantastically. So I'm just going to focus on two of these. Scaling processing capacity. There's a couple of patterns that we use that are simple but I think fairly effective. So the first is using stateless services. So the pattern works like this. We have a server process that accepts requests, but instead of processing that request directly, it forks a new child process, which actually does all the work. That child process sends a response back to the client, and then is cleaned up. That process is deleted, and the slate is wiped clean. And so this actually has immense benefit from an operational standpoint, because it means that if anything was going screwy with memory management or process management, it just gets wiped clean after every single request. Likewise, if a machine is behaving badly, that whole machine can simply be taken out of rotation, out of a load balancer, and we don't lose anything. No customer session, no state disappears because this machine didn't persist any state at all. So combining that with a pattern of read replica databases, if all of those services don't manage any state and don't have any resident state in memory, and they get it all from those read replicas, this is a pretty easy pattern to scale horizontally. Add more machines at the top under a load balancer, and then have them connect to whatever read replica is available, as long as they have the same copies of data. This pattern could basically scale horizontally indefinitely for as much traffic as you need to serve. So that's great. That's if you don't have to manage any state, but awkwardly, you actually do have to manage state very often. So this is probably a familiar picture. You got a bunch of applications all talking to a database through SQL, updating, inserting, deleting, committing. So I'm going to walk you through sort of the evolution of PayPal's scaling model. And remember, this is going back way, way back to 1998 when the company as a whole was significantly less mature in how we operated the site. So phase one, you run out of capacity, you go to Fry's and you go buy a CPU or some more RAM. This totally works. You know, these boxes that we bought had 64 slots for CPU, and we'd start out using 10 of them, so that's just tons of room left. As it turns out, though, that process doesn't actually work forever. And what we found is with some of these machines, even though they supported 128 CPUs, we'd actually discover that our performance would tail off and start dipping as we added more CPUs. And as it turns out, I think it's that the machines would spend more time synchronizing data between the CPUs rather than actually serving requests. So clearly this doesn't work forever. So phase two of our evolution was to split up the domains. You know, it was pretty easy to carve off risk data or customer service data or profile data from other pieces of data and host them on physically separate machines. So starting out with our one big database that everyone loved, we end up with a picture like this, which looks fine from here. But then if you start talking about connections from all the different applications, now your topology is a mess. And now, if one of those applications needs data from multiple sources, now instead of having one point of failure, you have 4. So this works from a scale standpoint, but ultimately kills you in terms of reliability and just how complicated it is to manage the system. So the phase we're at now, and this is something that's being introduced, is still partitioning, but just picking a different dimension to partition by. And really, the dimension you have to pick is the dimension that's going to grow the most. So in this case, we're partitioning by customer entities. And so here you can see a model where you put all data about US users in one instance, and separately all data, copies of the same domains, in a whole different instance. And this works really well when you have transactions that only involve a single entity. So, you know, you update a customer's credit card number or you change their password. We can do all that work just using the US entity. The question comes up, though, what if you have transactions that span entities, like payments, like cross-border payments? I'll touch on that later on. So let's switch gears a little bit and talk about development bandwidth. So when I joined PayPal, there were about 25 engineers, all in Mountain View, all in the same room, same floor. You know, it was like if I needed to talk to the customer service guy, it was like that guy over there. Scale forward a couple years, and you've got 10, maybe 100x growth in terms of the number of people that are working in the code base. And in my view, adding people to your code base is very similar to the logistics problem of trying to cram 3,000 people into a conference center. You know, you got to make room for them. You got to make sure that they are able to get in and out of places and they don't smash into each other. But in technology, it's a little different. So one of our approaches to letting people retain a small scope of concerns was to organize the code base by business domains. And you know, these are groupings of code that happen at the business logic layer and the web layer that were aligned with our different business units. So that whenever we had a new feature come up, it was very easy to identify, well, that feature is going to require changes in all these different domains. And that works pretty effectively. You know, the risk guys can stay in their risk domain and just focus on their code, keeping a smaller scope even though the entire organization is growing. We use service-oriented architecture pretty heavily inside, so very often these are actually services talking via RPC to each other. But the limitation of this, or the potential problem with this, is what about dependencies? What if, to do anything, with any one of these domains, you really require resources from every single other one. How do you prevent this nice separation, all these different rooms, from collapsing back into one big black hole? And so that's where really dependency management comes in. And I want to share with you these two examples of what I call dependency contracts. And this has proved really effective internally. So one is via our network topology. The entire way that our applications talk to each other is described and constrained in a single file. So using a DSL, we say that application A is allowed to connect to application B and C. Rather than having that sort of just in the mud of code everywhere where you can't necessarily find it consistently, it's in a single configuration file. So this makes it really easy to visualize the topology. It makes it easy to answer questions about what depends on what. And it's a single point of governance to make decisions about when certain domains are going to talk to each other or not. When dependencies between components don't take place over remote service boundaries, but they take place at build time, our build system also enforces this. So in the case of linking together C libraries, in this example here, we can say that library foo.a not only depends on bar.a, but it's only allowed to be packaged into the payment application. And so when we have one monolithic code base with a lot of different components in it all being built, this gives us like a little bit of a wedge in to start constraining dependencies and governing them. Maven has similar concepts in here. So, current technology, this is a pretty sort of standard concept. But I want to emphasize for any of you who are in technical lead roles or have the opportunity to influence this, how valuable it's been for us to have these properties, these relationships, specifically written down in a file rather than spread throughout the code base. So I'm going to move on to some design concepts, and they really revolve around state management. And here's my catchy phrase. It's all about transactions, baby. So if any of you guys are Puff Daddy fans, hopefully you got that reference. If not, I wish I hadn't said that. But let me break it down a little bit. So in terms of transactions, when we manage state and we work on the database, this is really big and weird, I'm sorry. You can break it down into three major categories. There's read-only operations. So for example, when a customer is loading and displaying their history page. There's when we update just a single entity. So that example of the US user just changing their password. And then finally, there's transactions that span multiple entities, namely payments. And so a principle that we had to build in to our forward-looking design is that atomic transactions can't span entities. This is a guarantee that you have to give up if you're used to working on one big database and doing all your work in one commit block. So going back to that pseudo-SQL of how a payment works, applying this principle, this pseudo-SQL doesn't fly anymore because you can't depend on being able to commit in one transaction both the sender's work and the recipient's work. So assuming they're partitioned over systems like this, what we end up with is breaking that work into three distinct transactions. The sender's debit on one system, committed. Recipient's credit on another system, committed. And at the top, some reliable process that orchestrates the whole thing and makes sure that eventually both of those two things happen. So now our scope for atomicity has changed. That debit actually may appear before that credit actually appears. But if you broaden your scope, I'll take questions at the end. If you broaden your scope, this entire set of work eventually reaches a consistent end state. If any of you guys are familiar with the Google App Engine storage APIs or even Amazon S3, you may be familiar with this constraint. It's usually sort of mentioned as like a very little side note. But when those storage APIs talk about entities or entity groups, they'll very often emphasize, we do not support transactions across entity groups. And the reason for that is because they're partitioning their systems behind the scenes by entity. And that constraint is actually super important for systems like that to be able to scale indefinitely, that you don't ever allow atomic transactions across entities because you just can't at certain scale. So now let's talk about the difficulty with this model. So those arrows in that case, in the PayPal case, are actually service calls. They're services that wrap around doing those debits and credits. But when we talk about remote service calls, using standard RPC, SOAP-like invocation, the worst problem is unknown. The worst problem, the crappiest problem, is you make a service call, you put the message on the wire, and then you don't get a response back. So in that debit case, we talk to the customer balance system, and then, yeah, we get a timeout. What happened? In terms of ultimately serving a customer request, either on the website or the API, we can't just say, sorry, customer, we don't know what happened. We have to take that unknown state and drive it into a known end state. So the technique for this is either resending the message and saying, hey, please retry this, please try it again, or if we wish it never happened, sending a message that has a cancel semantic. If you did this, please unwind it. This works, as long as your payment processing system or your system on the left can make sure to eventually drive those messages and get to a known state. But if you look at this and visualize how you'd actually write it in code, it's kind of a mess. It's kind of like it screws up your whole flow. Here's the service call that you really want to make. But then you have to follow it with all this backup stuff of if it didn't work, retry it, or if it didn't work, continue looping, and how do you make sure that that loop of retry or cancellation also happens? So our solution to this is to try to push that responsibility as much into the infrastructure as possible. So the way service calls can be made in this model now is not actually directly in code. But what the code does is it registers the intent to make a service call in a durable form. It's persisted to disk. And then a separate process actually drives those service calls being made and can keep track if we ended up in some unknown state, and then asynchronously keep on driving it forward or send cancellation if that's what the developer wanted. All of this, though, is predicated on that receiving system having an idempotent behavior on those service calls. It has to be that if the first service call actually did go through, and then we sent a retry, that we don't get duplicate debits or duplicate work in the customer balance system. So implementing some sort of idempotency guarantees on that remote service and that remote state management system is critical for it to integrate with a system like this. So let me shift gears and talk about just personally some of the things that I've learned as a technologist in my experience at PayPal. I joined PayPal right out of school, not knowing anything. And now I'm here talking to you. And this is sort of a little highlight of some of my philosophy that influences design choices. Infrastructure constraints shape the code. So what I mean by this are those little subtle differences in your state management layer, in your process model, in your memory model, that are really the only things you can guarantee will always be enforced. So if you have a big organization and you talk about governance processes, you talk about code review, talk about best practices, those might work. Sometimes it works at PayPal pretty well, sometimes it doesn't really work. The only thing you can really hang your hat on is what the infrastructure enforces for you. So how flexible your infrastructure is, how varied and broad the kind of things it lets your developers do with data, with state management, with memory, ultimately will affect what road bumps you hit when you scale. And actually, in this way, constraints are great. Preventing certain behaviors, like atomic transactions across entities, really save you down the road when scaling hits. And this, I think, is really why the cloud storage APIs that you see today are making good choices by forcing developers to abandon certain development models, like single tables that have giant indices that spread across that you can atomically update the whole thing for. While from a development standpoint, it may make solving certain problems a little harder, it ensures that you don't have to rejigger your whole application to scale it up 10, 100, 1,000x later on. More engineers means more logistics. I think PayPal didn't acknowledge the cost involved and the complexities involved with going from 25 to 250 and so on developers. Logistical problems about source code management, packaging, dependencies, these are all problems I think you can fundamentally engineer your way around. But that engineering has a cost, and that engineering cost has to be paid at the right time, because the longer you wait and the more people start coming into your code base, the more messy that problem becomes. So I guess as a recommendation to any of you, if you're in companies that are starting to grow, don't underestimate the importance of dealing with logistics of just how many people are working on your code base. It's something that will serve you in good stead and help you scale and be effective as you add people to your organization. Distributed state management is messy. There's no bones about this. It's a crappy problem. If you can keep your application constrained to a single database or data store with all your state in one place, it's a clean and happy world. We concluded at PayPal that certain systems of ours do have to deal with this problem, and so we're trying to push the mess of it as much behind the infrastructure as possible. But it's unavoidable that your application will have to deal with some of the constraints and some of the weirdness with distributed state management if you get to that point. So if you don't have to get to the point, then just avoid it. And then finally, buying or borrowing is faster than building. You know, like I mentioned, the early culture of PayPal was we're smarter than everyone else and we can do a better job. Combined with the fact that rolling back to 1998, there wasn't all this awesome open source infrastructure that you could just like whip off the shelf and have some crazy scalable whatever you want, memory storage, web framework, blah, blah, blah. But over time, the ecosystem has grown and is awesome. The amount of tools that are out there today are amazing. And it's great because in a small development team, the options that are out there let you really, really focus on what your differentiator is. So you can build that, invest in that, that's your secret sauce. All the rest, just borrow that. Don't waste your time solving problems that other people have solved that aren't the problem that differentiates your business. All right. So I'm going to wrap up. I want to leave like maybe 5 minutes for questions. I'll leave you with these two quotes that kind of roll up some of the culture about development at PayPal. And some reading material. This is a paper, Life Beyond Distributed Transactions by Pat Helland. I highly recommend you read this paper, and it's because it's a good paper for a couple reasons. It's really short, and it has pictures, so it's not one of those boring papers. It's just like text the whole way through. And if you read it, I think you'll be able to talk intelligently about distributed systems problems without a lot of effort on your part. So highly recommended, good for parties. Next is The PayPal Wars by Eric Jackson. Eric Jackson was a really early employee, earlier than me. And this is a fun walkthrough of some of the early management turmoils and some of PayPal's encounters with the mafia. So I'll leave it at that. Actually, I think a friend just told me that that book is no longer for sale. You may have to buy it on eBay. And it goes at a premium. So good luck finding it. I hope you have luck finding it. That's all I had. We have some minutes for Q&A. I'm more than happy to answer any questions you guys have about PayPal. And if we run over time, then I'm happy to talk afterwards. Yes, a question. This guy's a plant, by the way.
Earlier, you had the diagram of the split entities and doing individual transactions. So you're specifically not talking about XA two-phase commit transactions and reconciling through that mechanism. You're talking about a different mechanism?
I am not. Figured someone would ask me that question. I don't have to explain it. So we are not using the two-phase commit protocol for managing distributed systems for a couple of reasons. One is that two-phase commit attempts to hide completely behind the scenes the fact that you're actually dealing with different systems. And when it comes to preserving some veil of atomicity, that's fine. But in the case where one of those systems is actually unavailable, then your whole transaction is going to fail. And by managing this one level up at the application via orchestrated service calls, you actually have a lot more options in what to do in the case that one of those systems actually isn't available. You can partially start the transaction and finish it later. The other is that 2PC relies on locking resources on the remote sides. And we didn't want to commit to a solution that required locking-based solutions where resources were reserved. A question back there? Whatever, just run with the mic.
Any insight into the hot deployment? How do you guys manage deployments with new breaking changes versus non-breaking changes?
How do we manage deployments? I'm not sure I understand the question, but I can tell you that at one point we moved from a push model that, we moved to a push model that didn't require downtime. And so crucial in that is that if you're running, version N of your code, and all of a sudden, as your push rolls through the site, you got N+1 versions, your N+1 has to be backwards compatible with the data produced and maybe even the service calls in your N version code. So this actually usually requires more thinking on the developer's part. It's a problem that you don't have to solve when you can just shut off the site and roll new code and bring the whole thing back up. But clearly, not taking downtime is crucial to having continuous service. I don't know, did that answer your question? Good enough? Okay. There was a question over here.
Any comments on the reliable orchestration?
Yes, we built it. Much as I said that we didn't want to build things anymore, we decided to build it. And that was mostly because from our research, and some of these guys in the audience were in that with me, didn't find any commercial solution that really focused on short time transactions. There's a lot of orchestration products out there that seem to be tailored to long-running, like people scale transactions. So like, a customer complaint workflow that requires a phone call and then an email to be sent to the customer that might span over many, many days. But in the context of a payment, we want that business transaction to actually go from start to finish in under seconds. So in our research, we didn't find anything that was compelling that seemed to really hit the sweet spot in that short time frame. The other attribute of it was that by doing this way, we were actually able to build in knowledge of financial transactions specifically and where money was at any given moment. Because what this picture really represents is that money is coming out of the sender's system through the orchestration system and into the recipient system. So we were able to build in special knowledge that money is actually moving across these service calls.
First off, great presentation. Really enjoyed it.
Thank you.
2 questions. First one is PayPal has really good documentation, and it seems like the documentation is written at the same time maybe the code is written. And then the second part to that question is what type of peer review is done? Obviously, you guys are a fan of like a DevOps type scenario, but what type of peer review is done of the code before it goes to production? I'll let you expand on that.
Okay. Was there a question about documentation or just a comment? Okay. I wouldn't say it's anything really worth talking about. I mean, there's code review processes. We use Garrett is getting popular in-house. Some code gets reviewed more thoroughly than others. At the web layer, we want to encourage really fast development. Down when we're actually moving transactions around, we apply a lot more scrutiny to changes that get made. I don't know, it's probably not super great an answer. Other questions?
Yeah, okay, this may be my only chance to ask an actual developer this. I've used PayPal. I've been both programming with the API and actually using it for for commercial transactions for a number of years, and sometimes I realize, sometimes I experience going in, like searching for a transaction by somebody's email. It can be really slow. It can take a long time, even if it's just like a couple of months. And I'm wondering, like, do you guys have any? And it's a lot better than it was a few years ago. I remember there was a point, like maybe a couple years ago, where it took a huge bump up in speed, but it still takes a while. So I know you guys did something, but is it possible that you guys could take that to the next level, or what about speed issues?
Yeah.
And how to pre-cache or whatever you have to do? I don't know what your infrastructure is at that level.
Yeah, that's a good question. So historically, latency has not been a top technology priority. I mean, it's always been something we've cared about, but it hasn't been, a huge goal for us. And honestly, part of that has had to do with the fact that early on, PayPal transactions were largely eBay transactions too. And once a customer had committed to purchasing an item on eBay with PayPal, they were stuck. They were locked into that agreement. And so even if the PayPal transaction took a while, they were still going to come back and close that auction. But as we get out into different markets off of eBay, into all kinds of different use cases, latency is super, super important in those cases. So from an architecture standpoint and sort of across the company, latency is a huge priority. And the example you're talking about is one of many. Reading past transactions is a different problem than submitting and fulfilling new ones. They're all going to have tailored solutions. So the answer is yes. Hopefully, some number of months from now, you'll experience some improvements in that. I'm getting the neck chop sign. So why don't we wrap up? If you guys have more questions, I'll hang out here. I'd love to chat with you. So thank you very much for listening.